Since fats can only be metabolized via Krebs cycle oxidation, those free fatty acids we were talking about, a decrease in Krebs cycle intermediate serves to decrease the rate of ATP production from fat metabolism. So we've slowed down the glycogen-dependent, glycolysis-driven supply of all of those Krebs cycle acetyl-CoA, basically. So now we've slowed down the Krebs cycle machinery. So now we can't use the intermediates that are trying to come down from beta oxidation. So then you've decreased your ATP production from fat metabolism too. And thus you've decreased your muscle's maximum aerobic power output. So it's quite bad for your performance when you've depleted your muscle glycogen stores, essentially. I feel like this is something that people talk about when they're talking about working out and stuff like that, and they talk about carb loading. Have you guys heard of carb loading? Or in kinesiology, I once heard of carb loading. I feel like people not in kinesiology talk about carb loading. Okay. So this is a study, or sort of some hypothetical data, because there's no standard error points on here, but of someone doing endurance exercise on a cycle ergometer. So they're just cycling away. And what happens if they have a high carbohydrate diet? What happens if they have a moderate carbohydrate diet? What happens if they have a low carbohydrate diet? So here's time to exhaustion. So throw someone on a bike and tell them to go as long as they can until they become exhausted. And what's their initial muscle glycogen? I think it's probably not surprising, given what we just said about glycogen depletion at the level of muscle being real bad in terms of gumming up all of your machinery. If you have a high carbohydrate diet, so you've got really high initial muscle glycogen, then your time to exhaustion is the highest. And then conversely, if you have a normal carbohydrate diet versus a low carbohydrate diet. So you've decreased your initial muscle glycogen stores. So the whole purpose of carb loading is to try to get your muscle glycogen stores pumped up as high as humanly possible so that you've got that muscle glycogen to be able to keep you going. Good? Good. Do we need to go back to anything? Because we're sort of nearing the end. I guess I'm really mad if we finish early. Really happy, Finish faster. Okay. All right. So the amount of carbon dioxide produced per unit of oxygen consumed by the cell varies with the type of substrate used to produce energy. I have not inserted one of our big schematics again, but this makes sense if you go back and you try to interpret this with your schematic in front of you. This is going to make sense. So we can quantify something called the respiratory quotient. So the amount of CO2 produced divided by the amount of oxygen that's used or consumed can be used to estimate the relative contribution of carbohydrate and fat to energy production. So you've got your respiratory quotient for fat, palmitic acid. I think that was an example from the very beginning. I want to say 16 carbons. I don't know what's wrong with me. Oh my God, it's right there. That's embarrassing. Okay, pretend I didn't say that. So here's our palmitic acid, and then once this whole equation is done, we've ended up producing 16 carbon dioxide and 16 water molecules. And we've used 23 oxygens through electron transportation, in order to take the ATP out. So the ATP is obviously not in that equation, but that's really the important thing that we made from all of this, which we're ignoring here. We've created the 16 carbon dioxides, we have 23 oxygens. You do the math here, and you've got a respiratory quotient of 0.7. Am I talking fast? Was that good? You got it. Ooh, okay. I'm so excited, so nods. All right, what about carbon dioxide? So glucose. So we know we've got a lot less carbons over here. To break this down, we need 6 oxygen molecules. We end up with 6 carbon dioxide molecules. So again, do the math, and we end up with 1. So if you know sort of what if you're burning pure glucose looks like, it's 1, and the RQ doesn't exceed 1. Then as you go down towards fat, so if you end up with an RQ of 0.7, then you know that you're burning more fat than glucose. How is this helpful? Oh, look. what do we use that? This is what I was trying to do with my hands when I was talking about everything stopping each other. Okay, so the RQ assumes that the rate of exchange of oxygen and carbon dioxide measured in the respired air reflects gas exchange from macronutrient catabolism in the cell. So again, assuming that all of the oxygen that you're using and all of the carbon dioxide that you're producing is going to reflect macronutrient catabolism, which is exactly what we've been talking about. So the catabolism, or the breaking down of your carbohydrates and your fats. Hopefully not your proteins, but maybe your proteins. So during steady state conditions at rest and during low intensity exercise, when you have little reliance on anaerobic metabolism, VO2 and VCO2 reflect your cellular O2 and CO2. And then if you do that same math, instead of your respiratory quotient, you end up with your respiratory exchange ratio. Does that sound familiar to anybody? You guys? Yes. So you measure an RER when you're doing a VO2 max test. So that's your way of determining when someone's hit the end of their VO2 max test. What does that get above? 1.1? No. It's been a long time since I told them I'm not super into exercise. But you can measure someone's respiratory exchange ratio, and based on all of the substrate metabolism, when that value gets to a certain number, you know that they've hit their max and that they're like inputs. I am going to pause here because I would assume, what did you guys do last time? Wind gates, right? I think you're measuring VO2 max. Oh, you did VO2 max. Did you measure RER in that one? You were monitoring it? Do you measure it in your next one? Maybe next one, yeah. Anyway, you might come back to this. You might not come back to this, and then you'll see it one day if you ever run a VO2 max test and someone's quantifying your RER. You'll be like, wow, I think she talked about that. Okay, the last slide here, this to me is the least aesthetically pleasing slide. So, all right, we're going to talk about really quickly the bicarbonate buffering of metabolic lactic acidosis. When you produce lactic acid and lactate, from what molecule, first of all? Nice. And when would you start producing lactic acid? Under what circumstance? Right, exactly. So you don't have enough oxygen on board, you've gummed up your electron transport chain, your Krebs cycle, everything is slowed down. So now there's nowhere for that higher rate to go, so the body says, no worries, we'll just convert it into lactic acid or lactate. Okay, so here's our VCO2, so production of carbon dioxide, STBD standard liter per minute. And here's our, let me do this first. So here's our concentration of lactic acid, here's our concentration of bicarbonate. And this is as we're increasing exercise intensity on the x-axis there. So VO2 is increasing in terms of liters per minute. So during high intensity exercise, so above the anaerobic threshold, that's that AT there, lactate produced via glycolysis dissociates into a lactate ion, right here, and a hydrogen ion, which is not shown, but it would go up with the lactate ions because this is what's dissociating into. That wasn't a full sentence. It's dissociating into the lactic ions and the hydrogen ions, causing a metabolic or lactic acidosis. So you guys know pH, as pH gets lower, that means you have more what? Yeah, noise. You guys have taken chemistry, that's good. Okay. Alright, so in the blood, you've got bicarbonate ions, and those can bop around, combine with the hydrogen ions, and form carbonic acid, so that H2CO3. So here we are increasing our intensity. So here's our production of carbon dioxide. We're moving up. So lactate, the lactic ions were here, and as we increase our exercise intensity above the anaerobic threshold, now we have all kinds of production of lactic acid, which also means that we're producing the hydrogen ions at the same time. Back here, before the anaerobic threshold, we had our bicarbonate that was bopping along in the bloodstream. But then again, as soon as we pass the lactate threshold, now this is going down because it's scavenging all of those hydrogen ions. So there would be another graph looking basically exactly like this, showing the production of carbonic acid. And then at the lungs, the carbonic acid can dissociate into CO2 and H2O, and it's probably obvious what happens to that. You would then blow off your carbon dioxide. So the increased slope of the VCO2-VO2 relationship during strenuous exercise reflects the excess CO2 produced via bicarbonate buffering of the protons. That was a lot of sorry. And thus, the RER would rise to a level greater than 1 during strenuous exercise. Does that make sense? I've reached the end of my slideshow. I'm not that early. Does anyone want to sit and talk about these pathways? Okay, thanks a lot, guys. Darren's here next week. Be nice to him. Remember, it's not going to be exercise metabolism, it's animal absorption function. And I'm just going to confirm, double check with Dennis when the new labs are going to be. But it's going to be the labs that we're going to be in October. Is that your next lab? Yeah, so next lab is fine. It's the one after that. I'll send you a message. You'll get it. Oh, there is class on Thursday. There is definitely class on Thursday. You have to be here on Thursday. Okay. It's just going to be fully a month. Be here Thursday. Yeah, you know,